Hey guys, we're going to go over some more stuff in Unit 2. Today is day 16. Today's Wednesday the 23rd. It's an A day. And if you're on B day, then it'll be a different day for you guys. So it's day 16. Only a couple days left of the quarter. The quarter ends next Friday. Not this Friday, but next Friday. So today students are to complete the Unit 2 notes. So which is going to be this PowerPoint, but you're going to fill in the blanks. You can do that as you watch the video, or you can do it after. And then on Monday, I assigned you guys the density pre-lab. I had some that completed it and some that didn't. So if you haven't turned that in, I need you to turn that in today. Okay? All right, awesome. So Unit 2 is on properties of matter and change. So first we'll talk about physical versus chemical changes, which we've talked on before, so I'll hit it again. Intensive versus extensive variables. We'll talk about that and do some examples. We'll talk about the types of matter and classification of matter. And of course, we've already talked about density, so I'm probably not going to talk much about density. Okay. So here we go. So here's some vocabulary. So matter is anything composed of atoms, people, cars, food, metal, water, air. Anything that's not energy is matter. Mass is the amount of matter that's in an object, so how much stuff. So we're going to use a balance to determine that. All right, so number of grams, number of kilograms. All right, that's usually the unit for mass, is the gram, little g. The mass of a person would be the same on the Earth and the Moon. It's a fundamental property of matter, so it doesn't change. Now, weight is a measure of gravity's pull. All right, so you use a scale. It's similar to mass, but it's a little different. So your weight on Earth would be different than your weight on the Moon. That's because the pull of gravity is different, because the Moon is like 1/6 the size of the Earth. So your weight on the Moon would be different. You'd be able to jump higher. Volume. Volume is how much space something takes up. Okay. For solids, it's going to be a cubic centimeter, which means that it's length times width times height. Centimeter times centimeter times centimeter. That's why it's centimeter cubed. Centimeters times centimeters times centimeters. Or if you're talking about a liquid, then we're talking about a milliliter. That's how we measure volume. And a milliliter is actually the same thing as a cubic centimeter. We've talked about that with the density lab. 15 milliliters, 2 liters of Pepsi, 500 cubic centimeters, gallons. These are all units of volume. All right, measurable property. So if you have different variables that you can measure around you, different observations. There's two types. There's extensive properties, which depend on how much matter you have. Okay, so an example would be mass. So if I have an object and I weigh its mass, the mass of that object certainly depends on how much of that object I have, right? Because I'm measuring how much it weighs, essentially, right? So if I have more iron and I weigh it on a scale and determine its mass, the more iron I have, the more mass I'm going to have. So that's what we call an extensive property. It means that it depends on how much we have. Okay, so mass, volume, size, length, width, height, anything that deals with the size or how much of a substance we have, those are extensive properties or extensive variables. Now, intensive properties do not depend on the amount of matter. Density is an intensive property. Remember how I said that if I had a chunk of iron, if I had a tiny, tiny chunk that could fit in my hand, or if I had a chunk of iron the size of my car, either way, it's dense. It's very packed. The atoms are very packed together. That's what we mean by dense. It means it's surprisingly heavy for its size. And that doesn't depend on how much I have. I could have a little bit of iron or a lot of iron. Doesn't matter. It's still iron. So intensive properties depend on what the stuff is made out of. All right, so certain things are made so that the atoms are very close together, and it's very heavy and it's very dense. And then other things like wood or like the scrubbers, like a sponge, they're very light, right? And that's because of what they're made out of. It doesn't depend. I could have a big sponge the size of my car, or I could have a small sponge that fits in my hand that I would use to wash dishes with. Either way, it's light. Either way, it's not dense. So those are intensive properties. So intensive properties include temperature, density, and lots of other properties that depend on what it's made out of, but not how much of the substance you have. So that's an intensive property. It is independent of the amount of matter, or it does not depend on how much you have. So let's try some examples. Oh, not yet. Let's skip ahead and let's try some examples. I'll come back to this stuff. There we go. No, where is it? Did I put it at the end? There we go. This is what we want. Okay, so here's some examples. And I'll have to move this around in the PowerPoints. So intensive or extensive? Density. Density is an intensive property. So it does not matter how much stuff you got. Intensive. Color does not depend on how much of the object you have. If I have a small car that's red or a big car that's red, the color doesn't depend on how much car I have. It just depends on what color the car is, right? Now, how about weight? Weight is extensive, okay? If I were to weigh a car, if I had a big car versus a small car, and I determined the weight, if I put it on a scale and saw how heavy it was, well, the bigger car is going to weigh a lot more because there's more of it. So that's extensive. Volume is extensive. The bigger the object that I have, the more volume it's going to take up, the more space it's going to take up. Mass is extensive. The more mass of the object, the more mass it's going to have. Length is extensive, right? If I have a stick and I measure its length, well, the longer the stick, the more length I have. And so it depends on how much. If it depends on how much, it's extensive. Melting point is intensive. That's the temperature at which something melts, right? So for water, that's 0 degrees Celsius or 32 degrees Fahrenheit. And so I could have a big chunk of ice or a little chunk of ice. Either way, it's going to melt when it reaches its melting point, right? You put a big chunk of ice or a little chunk of ice out in the sun, it's going to melt at a certain temperature. Doesn't matter if it's a big chunk or a little chunk. So that's intensive. Depth is extensive because it's how, like, the size of something. Anytime we're dealing with size or mass or weight, these are all extensive. Okay. Size is extensive. Temperature. Does the temperature of an object depend on how much object you have? If I measure a cup of water in the room, if I had a little cup versus a huge bucket and it was sitting in the room, would the temperature depend on how much? It would not. So that's intensive. Viscosity is how easy a liquid can flow. So think about water. Water has low viscosity. It can flow pretty easily. And then you've got things like honey or syrup that are hard to flow, so they have a high viscosity. So it's the resistance of a fluid to flow. So intensive or extensive? This one would be intensive. It depends on what it's made out of, not how much. Conductivity is, does the substance conduct electricity or not? Metals conduct electricity, whether they're big or small, right? So that's intensive. Luster is how shiny something is, like a metal kind of reflecting back. How much does it shine? And that's intensive. A small chunk of metal is shiny, just like a large chunk of metal is shiny. Doesn't matter how much. Boiling point is intensive. Water boils at 212 degrees Fahrenheit, or 100 degrees Celsius. Doesn't matter if you have a bunch of water or a little water. It's going to boil at that temperature no matter what, because it's water. So anything that depends on what it's made out of is intensive. Some materials are magnetic, some are not, and so magnetism is intensive. Iron is magnetic, whether it's a little chunk of iron or a big chunk of iron. And then width is extensive, because you're measuring the size of something, which certainly depends on how much you got. Because the bigger the object, the more you have, then the bigger the width. So that's extensive. All right. So that's kind of our new stuff. Let's go back to physical versus chemical changes and review this stuff. We talked about this before, but let's hit it again. So physical and chemical properties. Physical properties can be observed without a chemical change occurring. So you do not need to turn something into something else. So you can just observe it. All right, so here's some examples. I can observe my desk and see that it's brown. That's a physical property because I do not need to change the desk into something else. The walls are white. I can see that without changing the walls into something else. Water, I've got my drink here, it's water. Water is a liquid. I can see that without changing the water into something else. So these are physical properties. Chemical properties can only be observed when a chemical change occurs. So burning paper, right? We know that paper is flammable. Flammability is a chemical property. How easy is it to burn? Well, you have to burn it to determine that, right? And so that's a chemical property. Photosynthesis is a chemical property. Rusting is a chemical property because rusting is a chemical process, right? And you're turning something into something else. Physical versus chemical changes. All right, so we can have changes and say, are they physical or chemical? Physical changes is where atoms are not rearranged into new substances. So a new substance is not formed. Physical changes include all changes of state. So boiling, melting, evaporating, freezing, all of those things are physical changes. And the reason for that is because when you freeze water, it's water when it's liquid, and it's still water when it's frozen. It's just changing forms. So it's just a physical change. You're not chemically changing that water into something else. It's still water, right? If you get an ice cube and put it in your mouth, it'll melt. And when you drink it, it's still water, isn't it? So it's a physical change. Physical changes include changes in size, shape, or dissolving. So if I tear something, break it, smash it, or if I build something, build it big, or make something, those are all physical changes because I'm not chemically changing it into something else. Now, another example of physical change is dissolving salt into water. If I take salt and put it in water and mix it, heat it up, it'll dissolve and mix with the water, and that is a physical change. It seems like a chemical change because it's dissolving, and it seems like a chemical, it sounds like a chemical word, but it's a physical change. Okay. Chemical changes is where the bonds are broken and you form new substances. Okay. Chemical changes are usually more exciting than physical changes because the chemical reactions happen. Something's actually happening. You're not just tearing a paper in half. Right? It's still paper, who cares? But if you burn the paper, okay, now we're talking. Now we get a different chemical substance. All right, so here are some examples of chemical changes: burning, rusting, decaying, and digestion. So if you burn something, you're combining it with oxygen, and it's chemically changing. It's turning into something else, right? You can't get it back. If you burn a piece of paper, try burning a piece of paper and then getting the paper back to its original state. You can't. So if you can't, it's a chemical change. Rusting, same thing. You take a nail that's nice and shiny and metal looking, you throw it outside for a couple weeks, it's going to rust. It's going to make that brown, reddish looking stuff, and you can't get the metal back. It's permanently changed chemically. Decaying, so if something's breaking down like mold or something's rotting, that's a chemical change. And then digestion, eating your food is a chemical change because your stomach acid is breaking it down. There are several indicators of a chemical change. So how do you know when a chemical change is happening? If you have heat that is changed. So if a substance gets hot or cold during the process, then it is a chemical change. Exothermic substances or exothermic reactions give off heat, so it's going to feel hot, and then endothermic reactions take in heat or feel cool. So if you got a change in energy or change in heat in that substance during the process, then that's a chemical change. All right, if you produce bubbles or fizzing, you're making a new substance, and so that's a chemical change. If you mix two liquids together and form a precipitate and a precipitation reaction, then that is going to be a chemical change because you're making a cloudy new substance. So this is a colorless liquid. This is a colorless liquid. You mix them together and voila, you get this yellow, cloudy, solid looking stuff. So if you get that, it's called a precipitate, and that's a chemical reaction because you're forming a new substance. And also the color change. If you see a color change, that means a chemical reaction is occurring. Think about when you burn paper. Isn't the burnt paper black and charred and looks different than what it was? That's a chemical change. All right, color change usually happens during burning. That's a chemical change because the color's changing. Burning paper, it goes from white to black. Another indication would be smell. If you have a change in smell when you do a chemical reaction, that is a chemical change because you're making a new substance that smells bad. All right, so tarnishing is where you've got a ring. So my ring here, my wedding ring that I've got, sometimes it kind of starts looking like crap and it kind of like tarnishes. That's what tarnishing is, where it starts to look like, it just doesn't look as shiny, doesn't look that great. So we want to think of, is that a chemical or physical change? And that is a chemical change because it's a change in color. Melting, if I take some water, some ice, and I melt it, is it still water? Sure enough, it is, so that's physical. If I evaporate water, that's physical, all right? Because if I take water and evaporate it and then collect the gas, if I cool that gas down, it'll reform the liquid. That's what condensation is, reforming the liquid. And so that's physical. Filtering, that's physical. Filtering is where I'm separating out solid chunks like mud. If I had mud and rock mixed with water and I wanted to separate the water to get the clean water out, I could filter the water and do that. It's kind of like filtering spaghetti. If you take spaghetti noodles with water, so you boil them, or your macaroni and cheese, you boil it, and then you put it in the colander or the strainer, you're going to get the noodles separate from the liquid, and so that's filtering. That's a physical change. You're just separating it. Density is a physical property, okay, because it's mass and volume, right? Viscosity is a physical property. Breaking something is physical because you're just breaking it into pieces. It's still the same thing. If I tear paper in half, both of the halves of paper are still paper. Dissolving is a physical change, and this is one that most students miss. Dissolving is not a chemical change. It's physical. Decaying is chemical. Digestion is chemical. Erosion is the movement of water, or the movement of like dirt with water, like a river, or how a river is going to carry dirt. So that's physical. Combustion is chemical. How much something is going to burn. All right. What else we got? So there's our answers there. And here's a challenge, multiple choice question. I'm not going to give you guys the answer. I want you to see. I want to see if you guys can come up with the right answer. So when each of the following is heated to 50 degrees Celsius and the temperature is held constant for 5 minutes, so that just means it's going to heat up sufficiently, which one will undergo a physical change? So if I take an egg and heat it up, think about what it turns into. Is that physical or chemical? Think about a steak. Think about ice cream. Think about cake batter. Which of these is a physical change? It's a good question. I like this question. See, and I'm interested to see what you guys come up with. All right, we talked about this. Now, classification of matter. And I'm just going to hit this real quick. So matter is broken up into mixtures, which is where you have more than one thing put together. And mixtures can be separated by physical means. I can physically separate a mixture. All right, if I have a mixture of dirt and water, I can filter it. That's a physical method, and I can filter it, and so that's a mixture. Now, pure substances can only be separated by chemical means. So we talked about physical and chemical properties. So now we can separate mixtures by physical methods, and we can separate pure substances by chemical means. All right, so there are two types of mixtures, homogeneous and heterogeneous. All right, homogeneous mixtures, they look the same. So what that means, or they're uniform or evenly distributed, like salt water, or like water with food coloring. Heterogeneous mixtures are different, okay? Which means they're not uniform, they're not the same. An example would be a cookie. So if I got a cookie, I got the chocolate chips, and they're black, right? And they're kind of soft, kind of gooey. And then I got the cookie, the rest of it, the dough, which is different than the chocolate chip. And so if you have two different things, that's a heterogeneous mixture. So a cookie, a salad, those are heterogeneous mixtures. Now elements, we know what elements are. They're on the periodic table. Elements are pure substances made out of one kind of atom. So if I have a block of an element in my hand, every atom in that block, or everything, yeah, every atom is going to be one kind of atom. All right, so an element is a pure substance where it's completely made out of one type of atom. Let's say it's oxygen. Oxygen's an element. And so if I had a block of oxygen, every single atom would be oxygen. That's an element. Now, a compound is more than one atom bonded together. So H2O, right? Hydrogen and oxygen, so that's water. Water is a compound. It's got two elements in it. More than one atom or two or more elements. Okay, and we'll hit this again. Mixtures, two or more pure substances that can be separated by physical changes. Homogeneous mixture is where two or more pure substances mixed evenly. So when you look at it, you can't see separate parts. So that means same. An example would be a solution. So salt water, sugar water, soda, coffee. Now heterogeneous mixtures, two or more pure substances mixed unevenly. So an example would be a fruit salad, pizza, sandwiches, cookies, where you look at it and you can see the two different things. Okay. An element is one of the 116 pure substances that cannot be separated by chemical changes or physical changes. And so an element is the simplest type of matter. Everything is made out of elements. All right. And so if you take something like a desk, you can break it down and separate it into elements, separate it into, and separate it, keep separating it, and eventually you'll get atoms. All right. And so those atoms cannot be separated by physical or chemical changes or properties or processes. And so those are elements. So here's some examples: hydrogen, helium, gold, mercury, lead, chlorine. And these are substances made out of one kind of atom. All of the atoms are one thing, right? If I have a chunk of lead and it's pure lead, the elemental lead, then that would be every single atom would be a lead atom. And I can't separate it by any means. An allotrope is the same element with different bonding. I'm not too worried about that. Diamonds and graphite. So diamond and graphite are both made out of carbon, but the forms are different. And so that's why diamonds are really strong and really hard, whereas graphite is actually used in your pencil lead, so it's very soft. So these two things are called allotropes. We could also call them polymorphs, and it's where they have the same element but different structure, different forms. Okay, and I'm going to stop there because this is a lot, and we'll hit this next time. Thank you, guys.